Let's begin with a very foundational concept, one that appears straightforward but is, in fact, the source of this entire challenge. Just how distant are the stars? Consider our position here on Earth. Our own planet is already a considerable distance from its neighbors. A trip to Mars, for instance, is an intriguing prospect, yet it demands months of travel. If your destination is one of the outer planets, you're looking at a journey that spans years. The Voyager probe, for example, took 12 years to reach Neptune. That's a staggering amount of time, wouldn't you agree? But here's where things get truly mind-bending. The gulf separating us from Neptune is minuscule, utterly insignificant when measured against the space to even the closest star. Allow me to frame this for you. Our nearest stellar neighbor, Proxima Centauri, lies approximately 4.25 light years from us. What does that signify? Well, light represents the ultimate speed limit in our universe, moving at 300,000 kilometers every second. It's a velocity that's difficult to comprehend. Yet Proxima Centauri is so remote that even light, the fastest entity known, requires 4.25 years to complete the journey. 4.25 years for a beam of light to travel that path. When you translate that into a more familiar measure, the distance is somewhere around 40 trillion kilometers. I feel the need to repeat that figure because it's crucial for grasping the true immensity of the scale, 40 trillion. To provide some context, Voyager 2, our swiftest probe launched in that general direction and traveling at its maximum velocity, would need more than 100,000 years to arrive at Proxima Centauri. 100,000 years! That duration is longer than the entire existence of human civilization. And here is the real kicker. Proxima Centauri is the star closest to us. Every single other star is even more remote. The next closest are many light years further still. Our own galaxy, the Milky Way, spans 100,000 light years from one side to the other. Can you grasp the implication of that? Traveling at the velocity of light, it would take 100,000 years simply to traverse our home galaxy. And our technology is not remotely close to the speed of light. We are nowhere near it. So the initial obstacle is the sheer, uncompromising distance. But that isn't even the fundamental issue. The true challenge lies in energy and physics. Let's consider what's required to propel an object to a high velocity. Imagine you want to send a spaceship, not even one carrying people, just a relatively small probe to another star within a plausible time frame. What is the essential ingredient? Energy. An absolutely colossal amount of energy. This is where the mathematics becomes fascinating, and I urge you to pay close attention because this is the point where fantastical visions collide with the unyielding laws of the universe. To make a spaceship travel faster, you must burn fuel. That fuel itself possesses mass. As you burn it, you are attempting to move not only your ship, but also the very fuel you are carrying. Consequently, to push that fuel, you require still more fuel. This principle is encapsulated in the rocket equation, a concept worked out long ago by the Russian scientist Tsiolkovsky. The rocket equation presents a deeply inconvenient truth. To achieve progressively higher speeds, the amount of fuel you need increases exponentially. Not just a little more, but vastly more, exponentially more. Let's imagine you want to get a spacecraft to 10% of light speed. That's roughly 30,000 kilometers per second. A speed that is still far too slow to make interstellar voyages practical, but we can use it for this illustration. The mass ratio, the proportion of fuel you need relative to your actual spaceship, must be somewhere between 1,000 and 1 million times the mass of the ship itself. 1,000 to 1,000,000 times. Contemplate what that entails. If you have a spaceship intended for a crew of, say, 100 or even a simple 1,000 kilogram probe, your starting fuel load would need to be 1,000,000 kilograms just for the initial push. But hold on, it gets more complicated. You can't simply speed up for half the trip and then drift. You must also have a way to slow down upon arrival. If you don't, you will just shoot past your target star and continue into the cosmic emptiness. Therefore, you need an equally enormous quantity of fuel to decelerate. Suddenly, your requirement is 2 million kilograms of fuel. And what if you plan to turn around and return? You'll need even more. Remember, I'm only discussing reaching 10% of light speed. That still translates to a 2,000-year voyage to Alpha Centauri. A significant portion of a human lifespan would be consumed by a one-way mission. If you desire to travel any faster, the fuel requirements grow exponentially. At this point, you might be thinking, what about more advanced propulsion concepts, like nuclear fusion rockets, antimatter engines, or solar sails propelled by lasers? These are captivating ideas that scientists have given very serious consideration. Some of them might be plausible in theory, but they all crash against the same fundamental wall. You still require immense quantities of energy, you still need a way to carry your propellant, and you are still bound by the laws of physics. Let me discuss a couple of these concepts and explain why they don't resolve the core dilemma. There was a concept from the 1970s known as Project Daedalus. This was a dedicated engineering analysis of what it would take to dispatch a probe to Alpha Centauri powered by a fusion rocket, basically using controlled hydrogen fusion detonations to propel the craft. And the interesting thing is, the scientists behind Project Daedalus were meticulous and strict. They considered only what was genuinely feasible with established physics. Their conclusion was that it might be possible to send a fairly small, uncrewed probe something weighing under 1,000 kilograms to Alpha Centauri in about 100 years, a century of continuous thrust and coasting. This means no living being from Earth could survive that journey. The crew would be born aboard the vessel, age, have offspring, and their descendants might perish before ever reaching the destination. Alternatively, you could send robots, which would arrive at their objective after 100 years of traversing empty space with no capacity to reverse course and return. That is the sober assessment of Project Daedalus, which was intended to be one of our more hopeful designs. And don't forget, this assumes we can overcome gigantic technical hurdles. You have to contain deuterium and helium-3 fusion reactions in the vacuum of space. You have to shield the ship from its own radiation. You must have engines capable of operating non-stop for a full century. These are not minor challenges. And it still requires 100 years to get to our closest stellar neighbor. Now, here is something that truly concerns me. So far, we haven't even touched on the human factors. We've only been discussing physics and fuel. But if you genuinely intend to send living human beings on one of these voyages, the difficulties escalate dramatically. Just think about it. You are sealed inside a spacecraft moving through a void. You are surrounded by cosmic radiation. I'm not just talking about radiation from our sun, but high-energy cosmic rays originating from all corners of the galaxy. These are particles with extreme energy that can harm your cells, trigger cancer, induce genetic mutations, and damage your DNA in ways we have yet to fully grasp. At present, we have no effective method to shield against cosmic rays. We can't simply construct thicker walls, as they would be excessively heavy and wouldn't be effective anyway. Cosmic rays would just penetrate them. You could try using a powerful magnetic field, but that would consume enormous power, and it remains uncertain if it would be sufficient. The shielding issue alone makes sending people on long-duration interstellar missions a monumental task, and that is just a single issue. You also have the problem of psychology. Picture yourself on a vessel with the same couple of hundred individuals for 50 years, 100 years, or possibly even longer. There's no going outside, no taking a stroll through nature. You are confronted by the same bulkheads and the same faces, day in and day out. Some researchers predict that the psychological toll would be catastrophic. People could lose their sanity. Violence might erupt. There could be a mutiny. We have no real-world data on what happens to the human mind when subjected to that kind of isolation for decades or centuries. Then there is the biological challenge. Your bones weaken in zero gravity. Your muscles waste away. Your immune system becomes dysregulated. Your eyes can swell due to fluid shifts in your body. We observe these phenomena in astronauts who spend just a year or two in orbit. Now extrapolate that to 100 years. What is the impact on human biology over such a timescale? We have no idea. And here is another factor. You have to ensure the spacecraft remains operational, all of it, for the entire duration. We are talking about complex machinery that must perform without a single failure for years, decades, or centuries. Here on Earth, if something breaks, you get a technician. In the depths of space, you are the technician. And if a life-critical system fails, you perish. You're confined to a machine hurtling through the cosmic abyss. If the life support system goes down, or the radiation shielding gives out, or the propulsion system malfunctions, you perish. No one is coming to rescue you. So now you can begin to appreciate what I'm getting at. Even if we could overcome the physics obstacles, and I am not convinced we can, the engineering hurdles are colossal, and the biological and psychological barriers might prove to be truly insurmountable. Let me touch on a few other notions people have put forward and explain why they don't function as smoothly as science fiction portrays. One of the well-known concepts is cryosleep or suspended animation. The premise is that you freeze the astronauts, placing them in a form of hibernation so they can sleep through the long voyage. This way, they wouldn't age, they wouldn't experience the psychological trauma of isolation, and their exposure to cosmic rays would be reduced. It sounds wonderful in the movies, but here is the catch. We have never been able to successfully freeze an entire mammal and revive it. We can cryopreserve sperm and eggs for later use, but a complete human being, with the intricate network of the brain, blood vessels, and organs, is a far more difficult proposition. And even if we could solve that challenge, which we haven't, you'd still face the issue of maintaining the cryogenic systems for decades or centuries. A single minor glitch, one interruption in power, and every passenger would awaken deceased. Some have proposed the idea of generation ships, immense vessels engineered to sustain human populations for centuries, with several generations being born and dying aboard the ship until their distant descendants finally reach a faraway star. It's a noble concept in theory, but it demands that we solve nearly every problem simultaneously. You would need a completely closed-loop, self-sufficient ecosystem within a spacecraft. You'd have to cultivate food, recycle every drop of water, generate your own power, and maintain the integrity of the entire structure for hundreds of years. You would also need to ensure humans remain psychologically sound across many generations while being confined within a metal container. It might be theoretically achievable, perhaps, but the engineering involved is simply mind-boggling. Then you have the more speculative ideas that physicists have entertained, wormholes, for example. Einstein's theory of general relativity does permit the theoretical existence of wormholes, which are like tunnels through space-time that could, in principle, allow you to travel from one part of the universe to a very distant point almost instantly. It sounds incredible. The issue, however, is that the types of wormholes predicted by Einstein's equations are inherently unstable. They would collapse in an instant. To prop a wormhole open, you would require something called exotic matter, which possesses negative energy and negative mass. We have never witnessed exotic matter. We have no idea if it even exists. And if it did, you would likely need a quantity of it comparable to the mass of Jupiter, and you'd have to place it with perfect precision. This is pure conjecture. It isn't technology, it's wishful thinking. There's also the warp drive idea, which originated with another physicist, Miguel Alcubierre. He demonstrated that Einstein's equations technically permit a bubble of space-time capable of moving faster than light. The concept involves contracting space-time in front of the ship and expanding it behind, allowing the ship to effectively ride this wave. It sounds magnificent, doesn't it? But once again, this necessitates exotic matter, and not a small amount, but tremendous quantities of it. And we don't know if exotic matter is real, if it could be stabilized, or if it could be manipulated to do what you need. So again, this falls into the realm of speculation. I need to be frank with you. These concepts are theoretically compatible with Einstein's equations. They do not contravene the laws of physics as we currently comprehend them, but they demand knowledge we do not possess, and technology we cannot even begin to engineer. They reside in the category of not proven impossible by physics, which is a far cry from being actually achievable. So, what is the takeaway from all this? If we are unable to surpass the speed of light, and Einstein's relativity suggests we cannot, then we are confined to relatively slow velocities. Merely reaching 10% of the speed of light would require technology we lack and energy sources we cannot currently harness. And even if we managed it, the journey to the nearest star would still take over 200 years. When I consider this from a pragmatic viewpoint, I am compelled to ask, what would be the motivation? Why would anyone dispatch humans on a mission lasting hundreds or thousands of years to visit another star? There is no economic justification, there is no practical purpose. You can't retrieve anything. You can't even maintain communication with Earth. Radio transmissions take years to travel in each direction. Between sending a message and receiving a response, decades could easily elapse. If I were a member of an advanced alien species seeking to explore the galaxy, I certainly wouldn't send living beings on these kinds of journeys. I would dispatch robots. Robots can be placed in a dormant state or engineered to withstand radiation. They don't require food, air, or emotional support. They are indifferent to a journey that lasts 1,000 years. And upon arrival, they can transmit data, perhaps construct more robots, and propagate throughout the galaxy. For interstellar travel, robots are orders of magnitude more feasible than living organisms. And this insight actually provides a potential answer to a long-standing puzzle that has perplexed scientists, known as the Fermi paradox. The universe is immense. It contains billions of galaxies, each home to billions of stars. The physical laws that permitted life to arise on Earth are universal. Therefore, from a statistical standpoint, there ought to be an abundance of life out there. Intelligent life, alien civilizations, perhaps even societies far more advanced than our own. And yet, we perceive no indication of them visiting Earth. We see no evidence of them colonizing the galaxy. The cosmos appears to be silent. Why? One possible explanation is straightforward. Interstellar travel is exceedingly difficult. It is so challenging that even highly advanced civilizations might choose not to undertake it. They might prefer to remain in their home star system. Or perhaps they send out robotic probes, but those probes simply don't come to our planet. Maybe they go elsewhere. The central idea is that the sheer difficulty of traversing the stars could explain why, despite the seeming vastness and antiquity of the universe, we have not yet had any visitors. Now, I don't wish to be entirely disheartening. There are a few things we could potentially achieve. We could dispatch unscrewed probes, very small ones. There's a current project called Breakthrough Starshot that aims to use powerful laser arrays to propel tiny spacecraft weighing only a few grams to 20% of the speed of light. These might be capable of reaching Proxima Centauri in approximately 20 years. That's a fascinating concept, and it doesn't violate known physics. But you are not going to fit a human onto a spacecraft that weighs a few grams. And those minuscule probes would be incredibly fragile. A collision with a particle as small as a grain of dust at that velocity could obliterate them. The strategy is to launch thousands of these probes with the hope that a few will survive the journey. Or, perhaps in a very remote future, we will uncover new physical principles that are beyond our current understanding. Maybe we will discover something about quantum mechanics or general relativity that unlocks possibilities we cannot presently conceive. Science is often full of surprises, but we should not depend on surprises. We must be honest about what we currently know. Here is what we know for certain. First, the distances that separate the stars are immense, so vast that even light needs years to travel between them. Second, accelerating any object to high velocities demands an exponential increase in energy and fuel. Third, there is a cosmic speed limit, the speed of light, which seems to be absolute and inviolable. Fourth, sustaining human life for decades or centuries in space means solving problems we have not yet solved and may never be able to solve. And fifth, the most speculative concepts, wormholes, warp drives, and other shortcuts through space on physics we do not yet understand, and forms of matter we have never seen. So, the next time someone suggests to you that interstellar travel is on the horizon, or that we will undoubtedly be sending humans to other stars within the next few centuries, I want you to consider these realities. Be critical. Pose the challenging questions. How fast is the proposed spacecraft? What is the required fuel load? How will the crew be shielded from radiation? How will they maintain their psychological well-being? And when they are unable to provide answers with concrete figures, when they retreat to ambiguous notions about future technological breakthroughs, you will understand that they are not approaching the physics with sufficient rigor. Now, I have spent a lot of time on the problems, and I'm aware that this might come across as negative. But I want to be very clear about one thing. I am not claiming that interstellar travel is impossible. I am saying that it is profoundly difficult, far more difficult than most people imagine. It is not something we will undertake casually, like booking a flight across an ocean. It demands a confrontation with the fundamental limits imposed by physics and engineering. But here is what I find compelling and what I wish to leave you with. The very difficulty of interstellar travel reveals something deep about our universe. It tells us that the cosmos is larger and more alien than our everyday intuition can convey. It tells us that the laws of physics are tangible and highly restrictive. And it tells us that we should adopt a sense of humility regarding our own position in the grand scheme of things. We are, for now, confined to Earth, this small world. The stars are magnificent to observe, but they are not our destination. And perhaps that is acceptable. Perhaps there is more than enough to discover and comprehend right where we are. The true merit of thinking critically about interstellar travel may not lie in the construction of starships. It lies in learning to think with clarity about physics, about energy, and about the natural constraints that define what is possible. And that kind of clear thinking is a skill that is always valuable.